Good afternoon. Welcome to COMSOL Multiphysics Heat Transfer Module, Introduction to the module itself. This is Hakam Al-Asoy, Technical Support Engineer at Energy Engineering and Agencies. We are the sole COMSOL Multiphysics distributor in the Arab countries. Today we're going to talk about the heat transfer module features, what you can find in the module itself, how we can use it in multiphysics, and we're going to demonstrate how to simulate a simple heat cross-flow heat exchanger. So let's begin. Heat transfer is one of the important phenomena that are present in most of engineering fields, if not all. In COMSOL Multiphysics, we have included in the material library more than 2,500 materials with up to 14 temperature-dependent properties. As also, we can have meteorological data, which is extracted from the library inside COMSOL, so you can specify certain regions with certain ambient temperatures and apply that in your models. You can use COMSOL Multiphysics heat transfer module to simulate conduction, convection, radiation, bioheating, and advection in any of your models. You can combine it with other physics or other modules as much as you need. Some of the examples you can use the module for is to simulate cooling of electronic chips. For example, packages of integrated circuits, PCB boards with the electronic components welded on them or soldered on them. You can see also how we can simulate the heat sinks and other conductors. You can simulate also phase change, for example, casting and welding. So you can simulate changing of the material from one phase to another and back to the beginning, the initial phase, like welding, from solid to fluid and then back to solid. You can also use it to simulate heat treatment or cancer treatment, for example, in bioheating tissues. So in COMSOL Multiphysics, there are in the library itself, there are some materials which simulate biological material. So, for example, heart tissue, brain tissue, and so on. And then you can also include whatever other material you would like to simulate by just specifying the material properties and then saving it into COMSOL. You can heat these materials using RF microwave, for example, or just electrical current as a heat source. You can find some of these examples available online on COMSOL.com, where, so for example, they're using a catheter to heat a certain region of biological tissue. So as for the example today, we're going to discuss how to create a cross-flow heat exchanger. The heat exchanger is very simple. It's made out of two stainless steel domains. So the first domain is this solid domain. The small channels are fluid or water channels. So you have a flow from beneath or in the lower plate from the left-hand side to the right-hand side, and in the upper plate from this side, from the front side to the back side. So this is a cross-flow heat exchanger. We're going to open COMSOL now and see how we can use it. So when I open COMSOL at the beginning, what I can find is my new page. So I'm going to start with Model Wizard. And since my model is three-dimensional, I'm going to click on 3D. Next, I'm going to go to Heat Transfer, Conjugate Heat Transfer, and click on Laminar Flow because I have a laminar flow in this micro heat exchanger. And click Add. This is the multiphysics package we're going to use. It's going to automatically add the heat transfer node and the fluid flow node, which is laminar flow node, and the multiphysics combining them, which is non-isothermal flow. So heat transfer in solid and fluid, laminar flow, and then the multiphysics combining them. And then go to study. Initially, I'm going to select a station study, and then I'm going to edit the study settings later. So done. In the parameter, I'm going to set up some parameters. So I'm going to set up the temperature of the cold side, let's say T T is going to be 300 Kelvin. By typing the unit between square brackets, I do not need to convert it from Kelvin to Celsius or the other way around. I'm just going to type a unit I use between square brackets, and it's going to be automatically converted. And T hot, TH, to be 330 Kelvin. I can omit the description for now to save time, but if I would like to type a description, this will be available for me when I open my model next time to remember what are these parameters stand for and why did I put them there. And the last thing is the flow velocity. So I'm going to call it U1. My flow velocity is going to be 50 millimeters per second. I know you might think it's like the units are very tiny, but this is a micro flow or micro heat exchanger, as you're going to see in the dimensions of the object itself. Next, I can go to geometry, create my first block. Before I create it, I would like to change the geometry units from millimeter to micrometers. So micrometers. And then my first block dimensions are going to be 800 micrometers by 800. And the height is going to be 60 micrometers. I don't need to specify the units as they are specified by default on the right-hand side of the field. So this is my first block. I need to create the channels next. So I'm going to go geometry, create another block. My second block, which is going to be also 800 micrometers by 100, and the height is 40. So it's less in height than the initial block. So I won't just cut through it. And then the location in the y dimension, so this is the y dimension, is going to be pushed or displaced by 200 micrometers, like this. So if I rotate it around, this is my first channel. I can create a single channel after one another by just duplicating it and pushing it around, or I can use the array tool, which I can find here in transforms. I can find array. By using array, I can create multiple objects, an array out of this object by just one operator, instead of just copying and pasting it and editing one after the other. So my array is going to be linear array just in one dimension, which is the y dimension. And I'm going to create 5 units. And the displacement between one another is 120 micrometers. Like that. So I've created 5 channels this way. I can also use the commutative selection to create a new selection. For example, let's call it channels, which I can use it to select all of the channels later, instead of selecting them one after the other. For example, when I'm defining the fluid domain, I can just find it in the menu, click channels, and then I can find it later. I've created my first part of my heat exchanger. Instead of creating the same exact thing by rotating it, I can use an operator called rotate, and it will replicate the same exact object another time by just skipping ahead. So rotate. I would like to rotate this for everything like that. By selecting Control A, I selected everything in this geometry. I'd like to rotate my channels and my cube. And then I would like to keep my original object. So by keeping the original object, I can rotate and replicate it this way. So in my axis of rotation, I can use the Cartesian axis in the X, Y, and Z. And rotate it by 180 degrees. I will also need to displace it upwards in the Z direction by 60 micrometers, like that. So now I have my other plane or my other part of the heat exchanger. So this are one side of the flow, and this is the other side of the flow. and between them are the two metallic plates here. And then I can just click build all. I have my model. Next, I can select my material. So I can go to material, add material. I can go to build in, look for water. I can also search for stainless steel. There is a lot of stainless steel here. I can use any materials I want. So in my case, I'm going to use, for example, aluminium. So this is available just on the spot here. So aluminium. For aluminium, I can select this, and then for water, I can go again, use my cumulative selection, which I defined earlier, clicking domain, and in the domain, I can find channels, which I named earlier, like that. So this and that, and then for water, the channels are selected. So this, what my model should look like for now. There is a missing property, which is dynamic viscosity for aluminum, which I'm going to fix later, so don't worry about that. For the heat transfer, I can go to fluid, select channel to be my fluid domain, and now you can see it's been excluded from the solid domain, which makes sense. Next, in the heat transfer, I would like to select flow conditions and inflow. Select these for my inflow. And then select another inflow for the other side. But I would like to define the initial temperature of this inflow. So let's call it T cold, T, which I defined earlier. And then select another inflow from the flow condition, boundary conditions, and then select my hot side. So these are my hot inlets, T hot, which was defined in the parameter earlier again. And then on the other side, I define also an outlet. So flow condition, outflow. These are my outflows. And I can also define another one. These are also outflows. So I have my inlets defined and I have my outlets defined like that. So this is just part of my heat exchanger. If I assume that this surface is replicated on the top, so the channel is just not like a rectangle, it's a square, and the same thing happens on the bottom, I can also use the symmetry boundary to include this by not including it in the geometry but including it just in the calculations. So I can assume that this is a symmetrical boundary like this, and zoom in to select the smaller spaces. And also replicated again on the bottom. So this is symmetrical, like a mirror, which is replicated with like a mirror on the bottom. like that. Next, I can go to my laminar flow. In laminar flow, I can exclude my solid domain because this domain is not flowing, and thus it was creating the missing property in the stainless steel. So the aluminium, sorry. If I go to my aluminium, I can see the missing property has been corrected. See, it's missing now. So there is no red cross here, we're good. For the laminar flow, I need also inlets and outlets and a symmetry boundary. So I'm going to go to here, inlet 1, again with the inlet 1. And this will include my velocity, which I used, U1. And I have inlet 2 for the other side, or the hot side, same velocity, U1. Next, I'm going to add 2 outlets. So outlet 1, like this, and then another outlet boundary on the other side for the hot side. This is for outlet 2. And not to forget my symmetry boundary, because this will make the calculations very different. So for now, before I define my symmetry boundary, if I look at the wall, it assumes that all of these sides are walls. So it's going to mesh and calculate based on that. But if I have a symmetry boundary, these are going to be excluded from the wall side, from the wall node, which makes it a continuous channel, like a mirror of this channel. Like this channel is mirrored again upon this surface, which will differ in calculations. So yeah, this is it. Next, my multiphysics is selected. Everything is appropriate. As for the mesh, I can use the physics controlled mesh, or I can mesh it using swept mesh, for example, for each and every domain. But this is a very simple model. We should not need such effort to mesh it. The physics controlled mesh, or the default settings for the physics controlled mesh, should be enough. It should take like a minute, minute and a half, maximum 2 minutes if I edit the settings right. Let me take a look at this area. Because we use the symmetry boundary, you can see the boundary element mesh are just on these 3 walls, but not on the 4th wall, because this is symmetrical. So it assumes that this is replicated as a mirror upon this surface, and thus there is no boundary layer mesh. As for the study, we can run it as is, but it will take a little bit more time. So we can simplify by just running it for laminar flow to more or less initialize the calculations, and then add another step under study to calculate the rest of the physics, which is heat transfer and the multiphysics of non-isothermal flow. And this way, it will more or less calculate much faster, like 6 times faster, six times faster. And then we can click compute and wait for the results. In the meantime, there is a question in the chat. We can look through it. Okay, your question is, do the materials have additional properties other than the ones that we can see in the settings window? You can add more properties by going to the material itself and adding properties if you want to. But the ones that you see in the window are the ones needed by the physics. So if it has a green sign next to it, then it's being used and it's okay. If it has a red stop sign, it needs to be used, but it's not available, then you have to fill it. Other than that, you can find it as just fields filled with information. And if it's not available in these fields, you can add more properties later. Yeah, the black window is the chat window, so I can remove it. This is a chat window. You can look into the chat window on your site to see it, but this is a chat window. I hope this answers your question, Carlos. As soon as the calculations are done, I can show you what I meant by the material properties. We're almost halfway done. Your follow-up question is, there is no hidden information that can change results. I'm not sure what you mean by hidden information, but whatever is being used for the material property. So if I look at aluminium, for example, whatever is being used in this calculations for these equations are just marked by green. All the rest, even if the missing properties, are not used. So if I would like to add more properties to these list, I can go to material property and then select one of these properties under these submenus and then click plus, which is going to add it later to the bottom list, and then I can edit it later. So if I go to equilibrium discharge, for example, radiation heat transfer, local property. So I can just add a plus, scroll down, and you can see this, which is not used and doesn't make sense now. So never mind. As for the other question, we have another question. How can I get the best mesh for each surface which gives the best accuracy? You can refer to the user guide. There is lots of meshing techniques you can use, but basically we try to cut down on the number of mesh, but at the same time not creating anomalies in the results. So if we have a very coarse mesh, we can find lots of anomalies in the results, like the transition between one value to another can be jagged. If you look at the temperature profile, for example, in this case, you can find a rough transition between one temperature to another, or one value to another. If you increase the mesh element resolution or decrease the size, it will produce a better plot, but it will take much more time. So it's basically depending on the user's experience and best case scenarios, or best case um, experiences from other users. If you're using something with frequency domain calculations, there are some equations that you should, or some functions that you can use to relate the mesh maximum and minimum mesh element size to the frequency you're using, or frequency you're calculating at, or the wavelength. And you can find these in some references. It depends upon what actually you're doing. So we can see the plots that we found here. For example, temperature plot. This is a temperature plot. So hot side is white, cold side is red, and by the time it reaches the other side, it's a little bit colder, and this is a little bit hotter. If the colors doesn't fit, so we can create our own result, or our own plot. So we can go to 3D plot group, and then we can select surface for temperature. But in this, we're going to use the rainbow plot. So plot. So cold is red, cold is blue, and hot is red, and green is in between. So this is one way to use it. You can also use a time-dependent solution if you want to. You can ramp up and ramp down the velocity, the temperatures, and so on.